Today, we're going to give you a brief tour of the TLS transponder landing system and its components. The TLS is a variation of the ILS instrument landing system that was developed by ANPC to overcome a very specific challenge. That is, how to provide the safety and capacity of a precision approach to thousands of airports around the world with terrain challenges that prevent the installation of common ILS systems. The main disadvantage of the common ILS is that it provides a static guidance signal with multiple antennas that must be precisely located on prepared areas that are often beyond the end of the runway and/or airport property boundaries, which makes installation infeasible at the majority of the world's regional and smaller airports. At airports with water, obstacles, or rough terrain at either end of the runway or along the approach, an ILS simply cannot be installed. In contrast, the TLS provides dynamic guidance to ILS receivers in the cockpit based on an aircraft's precise location in real time, and which is independent of a transmitting antenna's location and is insensitive to terrain and obstacles around the airport. All TLS components can be located on a small footprint of being the runway threshold in any airport environment. From an operational and a pilot perspective, the TLS approach is identical to a common ILS but can be installed where other systems cannot. The TLS interrogator works just like a secondary surveillance radar used by ATC to track and separate aircraft, but it has no moving parts. P1 and P3 signals are broadcast throughout the airport service volume to solicit replies from all IFR-equipped aircraft. A P2 signal is also broadcast to suppress replies from aircraft that are outside the airport's service volume. Aircraft transponder replies are received and interpreted in 3 dimensions by 8 TLS sensor antennas on 3 separate structures. Each of these antennas measures the precise distance to all cooperating aircraft, and when compared and combined, provide us with an extremely accurate positioning in azimuth, elevation, and range. The elevation measurement is far more accurate than the Mode C data used by surveillance radars, but is not accurate enough to provide guidance for approach and landing procedures. This structure is our calibration and built-in test system, which works around the clock to guarantee the accuracy and integrity of our surveillance tracking and guidance transmissions. It essentially functions as a participating aircraft that never moves and provides a baseline reference for all other aircraft surveillance tracks. Unless the system thinks this structure has moved, accurate tracking of all aircraft can be ensured. Once received, aircraft replies are digitized and processed into surveillance tracks that are saved for future review and analysis. These tracks are processed on 2 redundant computers in the electronics rack, utilizing dissimilar processors and operating systems to eliminate any risk of hardware or software computational errors. When an aircraft has been cleared by ATC for a TLS approach, the TLS will convert its unique surveillance track into precision guidance based on the offset from the aircraft's location to desired approach path, and instruct the guidance transmitter unit to transmit the appropriate guidance. The TLS is capable of supporting up to 4 guidance transmitters, which can then provide guidance to 4 approaching aircraft simultaneously over 4 discrete frequency pairs to the aircraft's ILS receivers in the cockpit. These transmissions come from a single UHF and a single VHF antenna, one for the localizer and one for the glide slope. With precision approach guidance and displays for both ATC and precision approach radar controllers, as well as transportable configurations, the TLS is literally an airport in a box that can be quickly deployed anywhere in the world in any runway environment.